It's a pleasure to be here again, and I'm going to talk actually about two series of work, one in collaboration with the first two authors and the one with the third one. So it's really two series of work, but we share a common theme. And I have some reference here. And okay. So what is the main? There is a main theme to these works, and it's some kind of a larger project we are working on with Marcos Katsoulakis, which is using idea of statistical mechanics and information theory to do something which is maybe something more numerical analysis, sensitivity analysis, or maybe uncertainty quantification, to use a word which is fashionable these days. And there will be, it's just an example, but maybe of some idea which might be actually useful. So I will give you two examples, and that's really the two parts of the talk. The first, I will imagine that I have a Markov process which is time reversible, which satisfies detail balance. And I will imagine that I am constructing some numerical scheme to simulate it. Okay? I will think of a stochastic differential equation, maybe Euler scheme or something like that. And when you do that, unless you're really, really lucky, your discretization, your splitting scheme, which is itself a Markov chain, is not time reversible, okay? Unless there is an accident. And what I would like to understand is, on the other hand, if you have a symmetry, there's a well-known tradition in numerical analysis to construct a scheme which respects the symmetry as much as possible. So I would like to provide a quantitative measure of how much the symmetry is broken, to see if it's bad or bad. Bad or good. And you will see the results are kind of amusing, okay, are kind of surprising. And the second example, which is really a different nature, but using also SDE, I will use, in some sense, the irreversibility with the goal to construct faster Monte Carlo methods. Okay, so I will imagine that I have a target measure, and I have a lot of algorithm going to that target measure. Usually you use reversible one, you know, but actually, I would say the message is that reversible algorithms actually are usually the slow ones. Okay, you can make it irreversible, make it faster. That's something which many people are interested in nowadays, and I will provide some example and a little bit of theory there. Okay. So I'm starting with some very general statement and very simple to remind people about reversibility. And time reversal is one of fundamental symmetry in physics. And for example, Hamiltonian equation of motion, classicals are reversible under, if you reverse time and velocity, you're invariant. Okay, so it's well known. I think of that as a pathwise reversibility. I have a path, and then I just inverse the velocity and go backward in time, and I get another path. I will talk today about something like more Langevin dynamics. Okay, so Langevin dynamics describe a particle in contact with a reservoir, and the reservoir is Hamiltonian, and then the big system itself of the particle with the reservoir is time reversible invariant. So, but this is a reduced description of it. Okay, so I just have Hamiltonian equation of motion, that is usual dissipation and noise terms. And this system is also time reversible invariant, but in a slightly different sense. Okay, so I can look at, if I look at the invariant measure, which is right here, which is Gibbsian, I've written the generator. You can just look at the detail balance as a property of the generator. It's the adjoint on the L2 space with invariant measure is self-adjoint modulo conjugation of changing with the velocity, the sign of the velocity. Okay. So what is the more interesting part for me is I think of that I have the Markov process implies a distribution on the path. Okay. So and the time reversal is that this probability distribution on the path is invariant under time reversals. Okay, time reversal here, the theta here is this one which reverses the velocity. Okay, well, it means a path and its time reversed version have the same probability. Okay, so which is a that's what usually probabilist means as reversible. Okay, so there's also another equation which I will look at, which is the high friction limit, where there is no momentum, there is just velocity, so you just have a gradient vector field plus Brownian motion, and this is also as an invariant measure, and it's also reversible. There is no velocity, so it's just simply self-adjoint. Okay, I will look at this equation too. Okay, so these are my reversible equations. And just to guide some motivation, that's not what I'm going to do, but just to explain an idea which came from physics a couple of years ago, maybe a long time ago. Okay, but people have been thinking about that a lot. Let me try to break the symmetry, this time reversal symmetry. Okay, and I can imagine that to my system I add a force which is in green, so nobody can see it, but it's a force which is not a gradient force. Okay. So if you do that, you just break the reversibility. This equation now is not time reversible anymore. Okay? And so there's a concept of physical entropy production, which is simply the force, the work done on the systems divided by the temperature. That's a physical concept of entropy productions. But more interested in this relationship here, okay, which relate entropy production, in that physical sense, to time reversibility. It's a simple computation using Girsanov that if you look at the Radon-Nikodym derivative of the path space measure with respect to the time reverse process, you get this formula, which is the exponential of minus the entropy production. There are boundary terms which are simply depends on the n times, okay? So they don't matter here, provided you can control them, which can be hard, but it's a technical issue. Okay, but I want to, in some sense, this intuition is that you get a why is that useful? Okay, so to me it's going to be useful, while you can be interested in the physics. That's what I want to discuss today. But you can be interested is that it's a you can simply compute, which makes that you can compute a relative entropy in path space very easily. Okay? Because what you have a distinguished observable, which you just need to control. So it's as easy as computing an ergodic average. Okay? It's computing the relative entropy rate. Maybe you take a limit. Okay? All right. So enough for physics. Now I want to change, and I talk about what I'm going to talk. Okay, so now I would think of a numerical scheme. I would think of the numerical scheme as an original systems plus some perturbations. Okay, which is not really true, but I think of it like that as an intuitive levels. So I think as the numerical scheme as something driving the system, maybe a little bit of detail balance, and I would like to measure how much. It's not going to quite work as well as that. Okay? And in the non-reversible, I will fix my invariant measure, and then I will look at stochastic differential equation with that particular measure. That will be the two different. But let's start first with numerical schemes. Let me give some generality first. So I imagine I have a stochastic differential equations, and I imagine my equation is ergodic, so I have a stationary distribution. Okay? That's the case I'm interested. And what are numerical schemes? A numerical scheme for me will be simply replacing this continuous times Markov process with a discrete times Markov chain. And usually I can imagine, they could be more general, but I can imagine they take these forms. So this is a discrete times Markov chain. We just have a function of the position of the previous step plus the Bn, which you can think as Gaussian random variable or something like that. Okay, and the x tilde with n, if tilde is a scheme, then it should be an approximation of the solution at times n times delta t. And delta t is the time steps. Okay? So that's what I want to think as numerical schemes. And I'm going to assume two things. Okay? One thing is that this numerical scheme is a numerical schemes that usually you get that it's good at short times. Okay? So for example, you have a weak error for suitable function f. You have an error for the delta t to some power. Okay? That's a weak order of the methods. That's very standard stuff. But I will also assume the following. I will assume that these schemes is actually good for long times. Okay? Is that actually the discretized schemes has a stationary distribution, and the stationary distribution are close to the original stationary distribution of the process. And there has been a number of results in these directions. I think the first one to do that was Thaler, and then there's by Mattingly, Stewart, Tretyakov, and so on. Gabriel Stolz too. And that actually you can show that your approximating scheme is actually good at long time too. Okay, and that's for me it's going to be an assumption. So you can prove it. It requires some work. Okay, so it requires some assumptions. Usually you need globally Lipschitz drift, otherwise usually you're not stable at long times. But to me, that's going to be an input in the theory. Okay, so it's an interesting. There are a lot of interesting problems there, but that's not what I want to talk about. So it's going to be an assumption. And so I have my original process, which is reversible. Now let me look at my scheme, and I'm just going to measure how reversible my scheme is. Okay. So how do I do that? So I'm going to assume, and which is true for all the schemes I'm going to look at, is that actually the Xn is the state space, and he has actually a smooth transition probability and smooth invariant measure. Okay, so and then I'm going to look at the following. That's if I look at if you have a probability density and multiply by the transition probability density is just the probability current. Okay, and I'm going to look at these particular observables. Mu is the invariant measure, and p is the transition probability, and I just look at the current from x to y divided by the current from y to x and take the log. So detailed balance means this ratio is 1. Okay? Therefore, if you have detailed balance, f is 0. Okay? Just by definitions. So in some sense, this is a measure of how much you break the detailed balance. And you can make a very simple computation. You just look at the probability of a certain path, okay? Just given by that, it's density. And then you just look at the Radon-Nikodym derivatives, and you find simply by construction is simply the exponential of that. Okay, I just have a log. The mu cancel. Okay. So the relative entropy of the relative entropy of the time reverse process with respect to the process, there should be nothing here. You just get that. And so you can compute it using this function f. Okay? So now I'm going to introduce now this quantity, which is the entropy production rate associated to the scheme. So it's going to be the relative entropy, and I'm going to divide by n, but I'm also going to divide by delta t, okay, to take into account that I have discretization of the delta t, so I should measure it as a function of delta t. And it's just by the ergodic theorem, you can write it like that. Okay, so it's an ergodic average. And okay, so at this point, you should be worried that in my function f, I have the invariant measure, which I don't know. Okay, but actually, it's easy to see that, of course, it cancels. Okay, so if I put that in there, it will be just the boundary terms. So I might as well just look at the ratio of the p tilde. Okay, so my important observable is the log of the ratio of one step and step backward. Okay, that's my favorite observable, and that's my quantity. Okay, and in the limit, so it's just an ergodic average, so it's easy to simulate, easy to compute, and I'm interested in the rate. Okay, so that's just it. So let me give now some examples. Okay. So yeah, I think I found these things amusing because I don't really understand the results, in the sense that, well, you will see. I do understand them, but I don't at the same time. So let's imagine first we start with an overdamped Langevin equations, okay? No velocity. It has invariant measure E minus 2v. And I'm just using Euler schemes to do it, okay? Simple schemes. So this is my transformation, okay? So these are just Gaussian with the right variance. And you can write down the transition probability density, that's easy. So you can compute this functional W along the path, okay? And it just take that form plus a bunch of terms which are boundary, which are just canceling the limit. And after the first theorem is that this entropy production for delta t, okay, so I just take the limit, take the rate divided by delta t. Actually, it's of order, the scheme is order delta t weakly. The entropy production is order delta t square, okay? So, and the way you do it, you do a Taylor expansion and you compute and you do some stochastic analysis. It's computation, okay? It's not terribly difficult to do, you just need to be patient. So the delta t square. And, okay, so I have some numerical simulation here, but let me pass them. And let's look at the second case. Okay, the second case, I look the same, a very similar equation, but now the noise is multiplicative. So I have a diffusion in front of the noise. Okay, so and with that form, okay, I need these correction terms. Otherwise, you write it as Stratonovich. But you get the same invariant measure. It's still time reversible. Okay, and you have I can do a Euler scheme on that, and it's the same thing. And you find an entropy productions which has much more terms. But the result is actually now the scheme is these schemes is also order delta t weakly. Okay, it has also work at long time delta t. But what you see is actually that the entropy production is not order delta t, it's order 1. Okay? So what does that mean? It means that the scheme is not anywhere close to reversible. Doesn't matter how small delta t is, the scheme is just not reversible. You just broke it. It's broken. Okay? And you can't fix it. And that was kind of unexpected. And I'm not sure I really understand why. And that's kind of a theme, is that I can compute these things, but I don't really understand why the result is the result I get, because the result tends to be a little bit all over the place. So that's why I think maybe this problem is more interesting than I thought at the beginning. Okay? So we have done very careful simulation to really capture that, and we really compute the constant and everything to make sure that we get that. So you can fix that by using, of course, better schemes, okay? By using Milstein schemes, which you have seen before in this conference. So if you add these extra terms, these are Milstein schemes, then you can show that the entropy production is now order delta t. In some sense, it's reversible again. Now, this is kind of messy to compute, okay? If you ever look at the transition probability of Milstein scheme, if you ever try to write them down, you will know why it's messy. So that's a fairly painful computations, and you have to catch. We had to catch a lot of cancellation to really get the right asymptotics. So it was not completely trivial. So, and okay, so that's it. So let me say a few things about Langevin equations. So let me look now at something with the velocity. So what are the schemes that you use for these equations? So here the equation is really Hamiltonian. So all schemes that are really good, in some sense, use what's called Sturmer-Verlet. Okay. Why do they use Sturmer-Verlet? Because this scheme is symplectic, it preserves energy, and it's reversible. Okay. So Sturmer-Verlet is a reversible scheme for the ODE itself. that's what you use it. So there is really no reason to use anything else. You can, but it's going to be really bad. Okay? So the way you discretize the Hamiltonian part is using Sturmer-Verlet, okay? Which is very stable and extremely good. And one standard scheme is called the BBK schemes, okay? Which I just doesn't notice that the K got the Nobel Prize in Chemistry 2 years ago. That's the name of the scheme. So what you do is simply some kind of split. It's a splitting scheme where you split this part of the dynamics, and then you act Sturmer-Verlet, which is itself a splitting scheme, and then you act again by the noise. So you make it symmetric. Okay? And so that's one of the most useful schemes. And I'm not going to give too much results, but I will just stay because I would like to move on to other things. But what you see is that, okay, so I have not written that these schemes is ordered, it's a second order scheme. Okay? So the error is ordered delta t square. Hmm? But the entropy production is actually ordered delta t with a coefficient which is very bad if you have large frictions. Okay? So in some sense, it's a very bad scheme. So that's something which has been, I mean, very bad. It's not that bad, but you can do much better. It's something which has been noted in a different context by Lime-Kuhler, which has also noticed the bad scheme. And but if you modify that a little bit by thinking of this thing as an operator splitting schemes, so you just write on the generator and write it as an operator splitting schemes, which simply modify this little coefficients here a tiny bit, okay, you get delta t square. So the reversibility is something which is very sensitive to little detail of the schemes, which is maybe not what I expected, but that's what it is. Yes?
You can modify that scheme in such a way that you produce exactly the Maxwell distribution, the Gaussian distribution with the temperature.
That's exactly what I mean by operator splitting schemes. Yes, if you can, what you do is you take that part of the dynamics and you solve it exactly because it's linear. And then you solve exactly that part and that part. So it's really that's exactly what I mean. Yes, you can do better, and there is no reason why you shouldn't do better. Okay, but people use these schemes all the time too. So that's another illustrations of the results. Okay. So I hope I convince you that that is maybe it's an interesting question, and there are many other applications you can think of because there are many many schemes which are reversible, and you want to understand them, so you can imagine plenty of other applications of the same strategy. Okay. So schemes we understand, and that's a paper we are writing, is operator splitting schemes are easy to understand, and we can understand. We have a nice theory about what happened to reversibility, but in general, I just have to compute, so, which is kind of weird because I don't know the result before I compute and compute and compute. Okay, yes, Stefan.
Just in general, with respect to look at the entropy production and this delta t squared, does it say something about how good is the scheme besides the fact that it's breaking down the...
Well, what do you mean?
The speed of convergence?
No, it doesn't. Okay, it really doesn't. No, it turns out that no, I don't think it has anything to do with the speed of convergence. This is very special what we do. Okay, so I would like to say there is something to be done there, but that's not the right way to do it. And I'm not sure I know, but this is something I'm thinking about.
So what is the entropy production for the continuous system?
It's zero.
No, but in general, when it's not reversible.
When it's not reversible, it's for which system are you? So what you do,
In general, let's say for your initial equation.
In general, you just take the measure of the process, measure of the time reverse process, and compute the relative entropy of these two, and then you divide by t and take the limit.
Okay.
That's the entropy production rate.
Yeah. But
Yes.
Some kind of stochastic integral, I'm wrong, or no?
Well, I wrote, for example, in the
Because when you do the Gestalt
Yes. Yeah, it can be. It can be. Sometimes it's a real stochastic integral, or it's just an integral, a regular integral of some observable. It depends on the process.
But then maybe this difficulty can come from the fact that this stochastic, this expression has no good continuity property. So you can.
Yes. So.
You can have limits which are different from zero.
Yes, I believe that, but I don't. Yes. Yes, of course. That's why I'm hoping half paths are supposed to solve everything. No, with that. So, no, but I think that problem I know. Yes, I have. I don't know how to do that, but I agree actually. So, okay. So let me go to the second topic. Okay, which is completely different. So we can restart from the beginning. It's the same equation, but it's a different problem. And all right, so I'm only going to do the overdamped Langevin equations. Okay, so I have a gradient vector field plus noise, and now I have my target distribution which I fix. And now I ask the following question: well, I can add many other drifts to my equations so that the stationary distribution is the same. Okay, that is drift in green. Okay. The only things I need to do, I need to pick the drift so that it satisfies that. Okay, so, and for example, I can expand the divergence. For example, what I can do is ask that the divergence is 0, and that C is orthogonal to the gradient of phi. Okay, it's not the most general, but this one will work for any temperature if you put a temperature there. So that's good enough for me. Okay, so for example, you can take simply you can take an antisymmetric matrix times the gradient, but there are many others that you can pick too. Okay, so there is a whole bunch of them that you can pick. So this is my results are not restricted to this particular class. Okay. And the point here I want to make is that the one which is reversible, meaning C equal to 0, that's the slowest one among all of them. And it's not in the slides, and we're writing a little paper there, but actually this is a really general principle. This has nothing to do with stochastic differential equations. Okay, so it's true for all class of Markov process. You take a reversible and you perturb it by something irreversible, which is a nice perturbation, and you will always get that. Okay, so yes, so I'm happy if you tell me that all what I'm saying today is trivial, because I think it's trivial, but it's maybe something which is not very much well known, or not known to everybody. I think it's not known to people who do practice. But all these arguments which comes are very soft. Okay, so no hard analysis coming. So this is not, of course, this is a fact which has been known, and I didn't invent that. Okay, so I learned that from the paper. The first, which from the paper by Wang, Ma, and Shi, okay, which is about the spectral gap. There are other papers related which I'll mention, and I think, which goes the following. Okay, the first thing is to look at the speed of convergence using the spectral gap. Okay, so as we know, the spectral gap measure, to me, will measure the distance between the the process at times t and the invariant measure, or it measures the decay of correlations. Okay, and these results, okay, say the following, which is a very easy result, and it's about a 2-line proof or something like that, which said that if you look at the generator, and this is the symmetric part, and now the fact that C preserves the invariant measure, telling you that this perturbation you add is antisymmetric in L2 is an invariant measure. Okay? That's what it means to preserve the measure. That means the perturbation is antisymmetric. Okay? That's an if and only if. So, and it's easy to show that when I'm talking about the spectral gap, so it's an absolute value of the real part. The spectral gap just increases. Okay? And it's a very easy proof. You can do it as an homework, really. Okay? Just you. And there are other examples. There is about at the same time as this paper appeared, there is a paper here where they actually look the case where there is no potential, but they prove also much more sophisticated results. They show that they actually add a vector field like that, which is divergence free. That's all what's needed. There is no potential. And they show that this eigenvalue, I should put the eigenvalue go to minus infinity, actually. Okay, that's the generator. So the spectral gaps becomes, this is not zero, it goes to minus infinity. That you can actually converge arbitrarily fast. Okay? If the flow generated by this vector field has nice ergodic property, weak mixing, is that? Okay. That's from the speaker before. Okay. So, and there are other kind of results in that direction. Is that if the flow is not weak mixing, then the spectral gap will just increase and then saturate at some finite value. Okay. Again, that's always u equal to 0. No potentials. So, okay. So the starting point from our work was actually not to do the spectral gap, okay, because we have a relative good understanding, and also from the point of view of, in practice, for people who use Monte Carlo methods, if you want to use this idea to design Monte Carlo methods, people in Monte Carlo methods don't use the spectral gap, okay? Because it's not the way you do it. It's not the way you simulate a process. What you do, you take an ergodic average, okay? And that the rate of convergence of this ergodic average is not controlled by the spectral gap, okay? So what people do in practice, they just compute the asymptotic variance, and this is their measure of the speed of convergence, of how efficient your algorithm is, okay? Because it's very awkward to, you don't take your system, simulate them 2 times t, and they take a sample of that by doing it many times. You take one trajectory and you just let it go, okay? So the spectral gap is not the right quantity. I mean, it's an interesting one, but not necessarily the right one, okay? And we took the point of view of actually looking at this ergodic average, and the convergence of ergodic average is just controlled by large deviations, okay, by the large deviation rate functions. So for example, I can look at the empirical measure of the process, and if I have a large deviation theorem, which I have in this case, I will have exponential convergence in the logarithmic sense. And this, the rate function, the Danskar-Varadhan function, will measure the rate at which you converge. Okay, so it's now a functional space of measure. Okay, it's the right quantity. And yes, before I continue, let me just give a concrete example, which is really silly. Okay, because you can just compute everything. So you have I'm on the circle. I have no potentials. So I add just a constant vector field. Okay, so it's not a gradient vector field because you are on the circle. And you can compute the rate. In that case, you can compute everything explicitly. Okay, there is no big deal. You see the spectral gap doesn't change. Okay, the spectral gap is 1, independent of delta. But what happens is that the eigenvalue become complex. Okay, and the asymptotic variance, on the contrary, just decrease because you have dissociation. So when you integrate, you get something which which decrease. So you see what's happening to what makes the asymptotic variance decrease is not necessarily the spectral gap could get larger. That could make the asymptotic variance become smaller, but it's also the oscillations. Okay, the fact that you're non-reversible, you have oscillations. That makes the asymptotic variance smaller. And here you can also compute the rate functions. And the rate function that's a form of the rate function for just Brownian motion on the circle. And that's the correction terms. You see it's order delta square, and you get this quantity. Okay, so it's the integral of 1 over p. And you see that it's increased strictly unless it's strictly increased unless p is exactly equal to. So p is the density of mu. Okay, I should say that p is the density of mu. So it's a rate function evaluated on measure with smooth densities. Okay. So now if you have in that case you have no potential. Now let me give you the general results we have, which is works if you have a potential. Then if you have a potential, you will have some more obstruction for the rate function to increase. So that's our results. Tell you that in general the rate function is bigger, and if mu has a density strictly positive, which has some amount of smoothness, then the rate function of the process with an additional drift is the original one, which you know explicitly. It's reversible. Plus these terms, which is manifestly positives, okay, where the phi c satisfies these elliptic equations, okay, and you can show easily that it's gonna. So these things is always non-negative, and we know exactly when it's 0. And it's 0 if and only if P is invariant under C, under the flow. What these things mean is the density P is invariant under the flow generated by C. So it's related to the constant of motion of the vector flows generated by C. Okay. So what it's if I write it like that, if I write P as e to the G, it means G plus U is an invariant under the flow divided by C, by constructions. But there could be other invariants, okay, and that gives you the obstruction. So if the measure here is invariant with respect to C, it doesn't see the perturbations, and then nothing increases. Okay, so it makes actually a lot of sense for that to happen. And oh, I'm sorry. So we also look at rate function for observable, which is maybe more interesting. So it's good to start with the empirical measure. But if you look at observable, you get a rate function by the contraction principle, and we get, of course, an inequality. And in some sense, we get that this thing is generically bigger. Okay, so we have strict inequality unless you have some non-degeneracy conditions, which again involve F and some possible invariant. U is and G are possible invariant under the vector field C. So what it means generically, okay, because it's pretty hard to realize. Okay, so generically you expect the rate function for observable to be bigger too. And after, so that's it. And then the last things we did is to look at the problem of variance reduction. Okay, so going back to the asymptotic variance. So we did that using the rate functions. So there is, of course, the asymptotic variance is just the curvature of the rate function at around the equilibrium value. Okay, and we show that again generically the asymptotic variance when you add a drift will decrease. We show actually that if you add a one parameter family of drift, then it's going to monotonically decreasing in delta. And here that's the only part where maybe my talk has something to do with the general theme of the conference. So you can think of that thing as some kind of averaging problem, what I'm doing here. Huh? So you have an Hamiltonian flow, and this extra vector field just average on the surface of constant potential. So if you have a good averaging principles, okay, which there are several papers by Friedlin, Wenzel, and Friedlin Weber, then you know that if you have some kind of averaging where you show that the divergence, the diffusion converge on the diffusion on a graph. Okay, so you just contract and you get diffusion on a graph, and you can show that actually the asymptotic variance will converge to the asymptotic variance of that process, generic process on a graph. That's how much you can go. That's all you can gain. The only thing you gain is just by averaging on constant energy. Okay. This is less or equal, yes. But it's, again, generically strict. Huh? So again, we have a condition. You can use this condition of genericity to show that actually generically you will be smaller, okay? Unless you're really unlucky. You have to be really, really unlucky. So we definitely haven't managed to get one observable which doesn't get smaller variance. Okay, so it satisfies complicated, complicated nonlinear equations. The F should satisfy complicated. It's some kind of nonlinear Poisson equations related to this U and this G. So, okay, and that's it. Yes. This one? Yes. So you can, okay, so after doing that, I realized that there is another proof. We do a proof really using a large deviation. So we really look at the large deviation functional and compute the mean. But you can do another proof, which in some sense is maybe simpler, just using operator theoretic consideration. Oh, I have another proof then. So yes, if you want to get just the variance getting smaller, you can do it in other ways. I agree. Okay, that's it. Thank you.
Other questions?
Yes.
At least for Markov chains, there's the relation with the work.
I don't think so. I don't think there's a relation. But I mean, they don't talk about spectral gap or anything like that. No, speed of convergence.
They connect the entropy production term with the.
Yes, but it's.
Functional.
Yes, but it's under very special conditions, and it only works. And I don't. Yes.
I think yes, there were conditions like for simple Markov chains in the state space.
Well, maybe there is. Yes, that's a good. Yes.
So, if you want to sample a Markov chain which is non-reversible already,
yes,
can you also improve your simulation with such a trick?
I don't know. Maybe, I just don't know.
Okay, thank you very much.